Hi, I'm Michelle McIntyre, and this is Lab 1 Constant Velocity. I am from Section NO3 for Physics 1. What I did is I rolled a ball across the table, this golf ball, and this is the video uploaded into Tracker. And first things first, obviously it's not starting at the very beginning because it was bouncing in the very beginning. So let's rearrange the window. Okay, so there's a video. It starts in the middle of the table. I started it at frame 59 and ended at 84 to account for the bouncing at the beginning and to cut out when it falls off the table at the end. First thing I needed to do was to calibrate it. So I used the calibration tool and set the length from one end of the table to the other to be 1 meter. And I did it at the same area that the ball was rolling, as from the angle it may seem that that area is shorter than the actual 1 meter. Next I took the axis and put the origin on the center of mass of the golf ball at frame 59 and adjusted the angle of the axis to line up with the ball's motion and line that up with the last frame, 89, with the center of mass of the ball. Next thing we need to do is create a track from the beginning to the end and make sure that it's rolling along the axis. So what we're going to do is we're going to create a point mass track, and you just hold down shift for each step. It'll automatically advance it. So what I'm trying to do is I'm trying to keep it as close to the axis as possible and try to really focus in on where the center of mass of the ball is. In the top right corner, you can see the data as it comes in, and the line is looking pretty straight with some minor deviations, which is to be expected due to human error, as I am human. So here it is, and the video is almost done. Also, you can see in the bottom right corner the data from the video, which includes the change in time for each frame, which is 0.033. Also includes total time and total distance in the x direction, which we will need later for our Python model. Okay, so now that we're done, let's play it. And as you can see, it automatically tracks the data and shows you where on the graph it is at that point in time when it's playing. Okay, so as I was saying, these are the main portions of this data we will need for our model in order to predict the motion we just saw and see if it truly is constant velocity. Okay, so this is our Python program. So first thing I did is I wanted to make sure that the position of the ball initially is correct. So let's try to find that. Okay, here we are. So the initial position, I tried to put it on the origin, but of course, human error, so it was off by 0.002. Sorry, wrong. Okay. And then this velocity in the x direction is from the total x divided by total time. Alright, obviously f net is 0. We got our ball velocity, which is just plus that vector, and then our ball position is going to be the initial position plus whatever velocity over the times the time that it's gone. Okay. So this is our model as it's played. That is the motion of the ball, and this is our graph. As you can see, it's a straight line, slope in the positive direction, same as mine. Okay, so what I did earlier is I took all of these lines that are now being highlighted, and I used those to extract the data into this Excel file. Oh, lost it. Give me 1 second. Here we go. Okay, and I also added the data from Tracker, so as you can see, it's time, Python, Tracker. Python is denoted by the orange line on the screen, and the gray is the Tracker data. So anywhere you see orange is where it deviates a little bit, but as you can see, most of it lines up. So now that it's lined up, you can see key equations, F net equals ma, acceleration equals change in v over change in t, average velocity equals change in x over change in time. Thus, if the slope of the position graph is constant, velocity is constant. If velocity is constant, then change in velocity is 0 and acceleration is 0. And if acceleration is 0, net force is 0. Some sources for error. Obviously, as I said, there were some errors. So based on the data, the object was moving with a net force of 0 with minor deviations due to releasing the ball in a weird way, angle of the camera, friction between the ball, uneven surfaces and bouncing, or not consistently marking the center of the mass of the golf ball while I was working in tracker. And as you saw, obviously, it's human error, so there are some discrepancies. Let's see. Yeah. What if I had not calibrated the video? The data would have been proportional, but it would not have been accurate for this model. What if I'd flipped the axis? The motion would have been in the negative direction instead of the positive. If I had not changed delta t in the Python model, it would have been really hard to compare to the other data, as the time would have been on a different interval. And that's it. Thanks for watching my video.